So we left off yesterday with Chapter 4 test, and I'm going to do a little bit of reviewing, and I'll take questions. So in Chapter 4, we had a large amount of theoretical material. It centered around theorems. And so in principle, if you know the theorems and can apply them, then you are good to go. This is some of the hardest material. I see that. This is some of the hardest material for students because instead of being calculations, it's really pushing logic, right? And so you have to check the theorem to see if the condition is met, and then you can draw the conclusion, or vice versa. If the conclusion is not met, then you can say that the condition is false. Okay? So what are our theorems? Well, we have the extreme value theorem. And you should be able to give the if and the then part for the extreme value theorem. What is that? If
continuous on the closed and bounded interval a b and
then
differential on
No.
That's me, darn it.
Continuous only. Yep. Then what?
Then there
There's
is an
an
absolute min.
Guaranteed absolute max and min, right?
Yep.
Good. If continuous. Speaking of continuous on the closed and bounded interval a to b, also if f is continuous on a to b, then the intermediate value theorem guarantees what?
F of x takes on every value between f of a and f of b.
Yep.
It's true.
Yes, it is.
Let's see here. So those are functions that rely upon, excuse me, those are theorems that rely on continuity. Yes, now some that also require differentiability.
Has Calc B learned the mean value theorem yet?
No.
Did you teach it to us last year, like during the same time as sandwich and all that stuff?
No, couldn't.
Okay.
Sandwich theorem is a theorem about limits. And until you have the derivative apparatus, the mean value theorem doesn't make sense.
Just feel like, just trust me, this works.
So there's a lot of that left.
This shorthand notation is actually very common. C1 meaning that you have, actually that's not really true. It's really D. There we go. If differentiable. If the function is differentiable. That's, yeah, that doesn't even really work. So forget that.
Just, no.
I was trying to shortcut it and it just didn't work properly. We have to do it correctly. So if the function is continuous on the closed and bounded interval, differentiable on the open interval, what can I conclude?
There is a C such that
Where is that C?
In the interval,
in
A to B.
the
Open interval.
Open interval,
A
right?
to B.
Such that
Such that
F
F prime of C
equals F
would be minus F.
minus F minus
Yes.
good.
Yes.
And then we can think logically this is a reversal. However, practically we can think of Raleigh's theorem as a special case.
One of the Raleigh's things you taught us doesn't exist on Google.
the corollary.
The corollary doesn't
It's always
exist.
been like
You can't find it on the internet. Like on the internet, it's like the Raleigh's corollary. You know, if you find like a sentence, like if you do this backwards, and like that's it. Like you
Really?
couldn't find Raleigh's
Yeah.
Or I
corollary.
found other corollaries that were by Raleigh that weren't that one.
Not the
That's not
corollary.
Interesting. Well, I gotta say the internet is very disappointing in some ways.
Yes.
The things that you cannot find on the internet are surprising sometimes, and the things that you find that are simply wrong
No,
on the
you're wrong.
internet, like really wrong, are also surprising.
What is
Like
this
normal
existence
things.
theorem?
Something exists.
Yeah.
We were just proving that something existed so that we
Okay.
could use it.
So Raleigh's theorem has these two conditions, and it also has the additional condition that f of a is equal to f of b.
Yes.
If I take that and immediately put it into mean value theorem, I get, therefore, there exists a C in A to B such that f prime of C is equal to 0. From a practical computational standpoint, this makes a whole lot of sense. From a logical standpoint, it doesn't. Because we use Raleigh's theorem to prove the mean value theorem. So we can't really logically take Raleigh's special case of mean value theorem because mean value theorem sits on top of it. So how did we prove Raleigh's theorem? Well, we proved Raleigh's theorem, now working backwards a little bit, by observing that if a function is continuous and differentiable on A to B, closed and open respectively, then it, and if f of A equals f of B, then it has to have extreme values, extreme value theorem, and the extreme values cannot both occur at the endpoint unless the function is constant. Therefore, it has to have a local extremum, and local extrema only occur at critical points, and the critical point has to be of the first kind because the function is differentiable in the open interval, therefore there has to be a horizontal tangent. That's the proof for Raleigh's theorem. Yeah.
So why does this theorem, like, why is it even used if the other theorem says there's minimum and maximum values? Why can't you just use that theorem instead? Like, why do you use this?
Yeah, so what math often does is it builds up small pieces that are useful, right? So you're exactly right that the extreme value theorem implies Raleigh's theorem together with local extreme only occur at critical points. But Raleigh's theorem now turns out to be a useful result because there are all sorts of situations where I want to say, hey, look, there has to be a horizontal tangent in there somewhere. Now, we haven't seen a lot of those yet, but we shall.
What I was trying to say is, why wouldn't you use the extreme value theorem to prove that? Why would you use Raleigh's theorem?
Oh, I see.
Like, what's the point?
Yes, yes. So the point of Raleigh's theorem is actually to get a value for f prime rather than to say there's an extreme value.
Oh, so you can find the C.
Yeah, I'm focusing on the value of the derivative rather than focusing on the fact that I have an extreme.
Okay.
Yep.
On our exam, are you going to expect us to prove things or just be able to know and use the theorem? Or both?
Well, I think you just repeated yourself. So using the theorems, one legitimate use of theorems is to prove things.
No, I mean, like,
If I
prove the
have us show that, it will be 1 or 2 steps, not complication. However, being able to prove Raleigh's theorem is a good skill to have.
Would this be old AP test format like last year, where it's like
Probably. Yes. I need to kind of do a. Well, I'm assembling everything today, so there it is. Out of pieces, Franken test. Thanks. Now, I mentioned this theorem, local extrema only occur at critical points, and so we have 2 definitions in a theorem that we need to account for here. Local extrema. What are local extrema? Define it for me.
First of that line
Oh,
changes from positive to negative.
wait.
Yeah, that's a good first D test, but I'm asking what is a local max rather than how can I tell it?
you value of f of c that is greater than f of c minus 1 or f of c greatest 1.
The value of,
The largest value of C on an interval.
okay, but what is it that makes it local rather than absolute?
This is on an interval.
It's the open interval.
And not.
On an open interval, that's exactly it. That's right, if it's a max on an open interval.
I was trying to define max, and then I was gonna put open interval.
Yep.
I didn't know it's used by definition.
In the definition.
X equals C is a critical point if.
Prime
F
C.
prime of C equals changes sign.
Nope.
Equals
Zero,
zero.
zero,
If F
or
prime
it
of
does
Or
not
it
exist.
doesn't
C or
exist.
does not exist. And these are
Wow, Christine.
critical points of the first kind and of the second kind respectively. Now, why do I say that local extrema only occur at critical points? So, this is another theorem that's worth knowing how to prove. We say that local extrema only occur at critical points because if f prime of c is greater than 0, then that immediately means that our function is increasing through c. Right. What I'm literally saying is that my derivative at c is greater than 0, right? And so that means that there is a neighborhood around c for which f of x minus f of c over x minus c is greater than 0, right? And so we have only two possible cases. If x is greater than c, then that implies also that f of x is greater than f of c. In other words, if I go to the right, I go up. But if x is less than c, so I have a negative value here, then I also have to have a negative value on top there. F of x is less than f of c, so that if I go to the left, I go down. So increasing through c, what does that mean? Well, that means that f of c is not a local max, because if I go to the right, I can find higher points. And it's not a local min, because if I go to the left, I can find lower points. And so if f prime of c is greater than 0, then that means that f of c is not a local max or min. Because for any open interval that I draw around it, I can find f values that are both larger and smaller than f of c. Does that make sense? Likewise, if f prime of c is less than 0, same argument, the different signs, then f of c is not local max or min again. So, use the logic on this. If f prime of c is either greater than 0 or less than 0, then f of c is not a local max or min. So if f of c is a local max or min, neither of these cases can happen. What's left? F prime of c is equal to 0, or f prime of c simply doesn't exist. In other words, x equals c is a critical point. Does that make sense to everybody?
Why does f of x minus f of c over x minus c have to be greater than 0?
Ah, great question. This is the key point here. You agree that the limit has to be greater than 0, right?
Yeah.
Because this is literally the definition of f prime of c. Okay? So now, what does this mean? This means that for any epsilon that I choose, that there is a delta, so that this quantity right here is within epsilon.
Okay.
And because we have 0 in particular, that means that around C, I can find a delta neighborhood so that my epsilon I choose so that it's so that the distance is greater than 0.
Right, this is basically just saying delta y over delta x is greater than 0.
Yes, exactly. That's it. Since the limit is greater than 0, then within a neighborhood, say it's some value d, right? Then I can take an epsilon that is smaller than d, so that all of my quotients have to be within d plus epsilon to d minus epsilon, which are positive numbers.
Are we going to have to do epsilon and delta calculations on that thing?
If so, it'll be bonus material.
Okay.
Cool.
The probability is high that I'm going to throw something like that on there, because what happens for us when we do Taylor series is and series in general, is we come back to the notion of epsilons to talk about convergence. Okay. So if f of c is a local max or min,
If you realize your plans are here tomorrow.
then f prime of c is not greater than 0. F prime of c is not less than 0, which means that x equals c is the critical point.
Especially when you maintain your.
Okay, and that gives us what we needed for Raleigh's theorem. Now, Raleigh's theorem gives us mean value theorem. Everybody should know how to do that proof. It's in your notes, and we'll go over it a second time. The mean value theorem is crucial because it gives us our 2 derivative tests for local max. And here I want to be really careful about a thing that some of you are still kind of shaky on, and that is local extremum tests versus absolute extremum tests. These two are really, really different from each other. The arguments that we make are really, really different. And they're really different because in the local extreme tests, all I'm trying to do is to see whether or not I can find an open interval for which I've got a max and min. Whereas for the absolute, I'm trying to look at the entire number line to see what the biggest one is. So what are my options for local extrema tests? The first D test or the second D test? And everybody needs to know the strict legal language here. What is the first D test?
That's what I was thinking about.
That was what you said. Yep. If f prime of x changes signs, plus to minus, and x equals c.
You erased our party from math book?
No, that happened yesterday. Beth Ann researched it.
I didn't erase it. No, I went to put it back up and Mr. Taylor erased it.
I did. I thought it was crossing over into potential hoax at this point.
I really wanted some kid to be like, oh, that must have been erased. That must mean that everyone's going already.
I got no problem with Chapelgate students getting punked a little bit, but I got a problem with it happening on some random stranger's doorstep.
Probably not a stranger, you probably know.
Don't know. Please notice that this is really interesting right here. All that we require is that there is a sign change. Does that imply that f of c is a critical point? Well, it should, because local extreme will only occur at critical points. And actually, if you think about it, there's only 2 possibilities for sign change. Either we go through 0, or we skip right past it. So yes.
Yeah.
What is the language of the second D test?
But it's f prime of c equals 0.
Yes, we have 2 conditions.
And then and
And-
f double prime of c is greater than 0. Or yeah, or less.
All right. So what is greater than 0? Tell me.
It is.
So it's a mean.
Yes, is a local min, and you want to use a nice little y equals x squared curve
And
to
it's constant.
keep your head straight on
Yeah,
that.
it's constant.
Yep. If f double prime of c is less than 0, then we have f of c is a local max. What if f double prime of c is equal to 0?
So the second D test fails.
Yeah, that's right. This is a key point that everybody needs to know, and that is that we have no information from this.
Third D test. Oh my God.
Actually, it's even D's. So if your 4th D is positive or negative, then that would tell you the same. If your 6th D is positive or negative, that would tell you the same. Yeah.
You have a function that's derivative of 0, but it's positive.
What if it's like, signs on that difficult of a function, just keep going out 1,000 times.
E to the x.
Mr. Gale, can you take the derivative of I?
Yes,
It's okay, you don't have to lie.
Well, if they would take the derivative of like, it's a constant. That's lame. They wanted to
A constant,
say,
oh, that's
well, it's just a
lame.
number.
yes.
But not real.
So, but the question that you're really asking is a really cool question. It has a really cool.
What is the slope of x line?
Yeah, it's
Looks like
What-
I.
can you take the derivatives of functions of complex variables, and if so, what do they mean? And it turns out there's an entire branch of mathematics called complex analysis that deals with that question.
So you can make it.
So the answer turns out to be yes, and the existence of a complex derivative is a stronger thing than the existence of a real derivative. If a function has a complex derivative and has a continuous complex derivative, then it will actually have continuous complex derivatives of any order. So if I have f prime of z, and it's a continuous function, then I'm guaranteed that f double prime, triple prime, quadruple prime, all exist, which is pretty cool.
What does a complex
Maybe
derivative?
I'll
What's
take
an
this
example
liberty.
of one? Like, is it some like crazy, ridiculous thing? Is
E to the I.
It's actually not very complex. So if you have any functions that are in the standard family of functions, if you apply them to the complex plane, their derivatives are exactly what you would expect. So the derivative of sine z is cosine z, the derivative of e to the z is e to the z, etc. But the meaning of it is a different picture because now your domain is the complex plane and your range is the complex plane. So instead of having x and y axes, you now have plane mapping into a plane. So it gets a little neat. And it also, have any of you ever seen the Mandelbrot set? It's sort of a highly colored diagram that looks like circles attached to circles, with sort of, or how many of you have ever heard of fractals?
Yes.
Yeah, so fractals are actually generated via complex variables. Okay.
What's that word?
Absolute extremitess. I've got, I need to find the max or min for a function, I need to justify it. What legal language can I use?
If A is greater than 0, well, you have to like use both A. Like, I know how to say it, if I'm writing it out, you have to have it.
Okay, well, what are the names of the two kinds of arguments that we can use? We can use an argument from,
values,
specifically, what values?
the critical points and endpoints.
There you go. We can make an argument from critical points and endpoints.
And from the
And how does that argument go?
plug in the critical
You set
points.
f prime equals 0 and find all the values.
Yep.
C at y.
I've done that.
And take the inputs.
Yep. Yeah, that's right.
Pass out.
I think it'd be
Okay. So this is one argument that you can use. This is usually necessary if you have more than one critical point, right? Unless you can exclude some. How could I exclude some? Well, if I have a critical point that is a local minimum, then it can't be an absolute maximum, right?
If the
a valid point.
So very good.
I got the next one too. If you can state that f prime is greater than, like, is greater than 0 for just greater than 0, not like on a
Yeah.
down and like less than 0 from like the other side.
Yeah.
That makes
Yeah.
So argument
From F prime.
from the sign
Oh, hello.
F prime. Okay.
It's my own place.
And here's a good little model problem. Find the absolute max and min of f of x equals x squared on -2 to 2. And at this time, I would like for you guys to solve this problem. You already know the answer probably. And it will give you a chance to practice using both of those arguments. Go.
Can I erase your math club?
Yep.
So it's
Siblings.
no argument.
No.
So it's a geometric series. John Clever probably might say so.
And until we know how to do it, it's like this.
Well, yeah, there is a certain amount of that, isn't
I
there?
feel like if you showed like elementary school kids calculus, they just laugh. Like, that's not gonna happen.
Number.
Like, no.
That's the
I
other.
don't
Well,
think- Yeah.
actually, we do ourselves a disservice by pushing calc so late. My daughter, my 9-year-old, was asking about rates of change. I mean, she didn't say, Daddy, tell me about instantaneous rates of change, but she was asking about the constant. And lo and behold, I can explain it.
Did she understand it?
Yeah. I didn't give an explanation that involved limits.
It's too much.
You like draw out all the little symbols, you're like limit integrals.
She would. My other daughter would go, oh, cool.
I feel like if you told a 5-year-old that you can add 0 and get a different answer.
They just be like,
You'd
no.
be
They'd be like, no, you're just joshing me.
Maybe.
You like zeros, honey.
So my little sister has this, she's homeschooled, and she was doing science something last night, and they're doing, like, she's on like a physics unit in science.
I want you to answer this question.
Oh,
You got it?
Yeah.
He thinks he's got it. All right, go ahead.
Okay, I know what he's talking about.
Go.
I prefer to.
So the critical points, there's only one, or within the open interval, there's only one, and it's at 0.
Yeah.
And it is an absolute minimum, or local minimum, so we can neglect it. It's 0 at 0.
It asks for both.
Max
Oh, that is the max.
That's the
Oh,
most.
so well, I'm going with max first.
Okay.
So we
Okay.
can disregard that for the max, because clearly if it's
Okay.
local min,
Why
it
would
can't
you
be
say
it. So then the endpoints you can evaluate, and then each endpoint is 4, because it's 2 squared, negative 2 squared. So if you take those 3 into account, then there is no absolute max, because both of those are tied.
You have dual max.
Can you have more than one max?
No, you have one max and it's
You can, no, you can't have more than one max, but you can have more than one location where the max
So one
occurs.
max is 4.
So the absolute max
Yes.
value is 4.
So,
You said something, I can't
I'm
remember what you
sorry.
said.
they are both, that's like, they're both the absolute max value. The absolute max value occurs at both of those
Okay.
max values. And then for min, it's, you can, using those same 3 points as before,
Uh-huh.
you can, there's one min and it's smaller than that, because you have those same, you have to evaluate the same 3 points, so you have 0, 0, 2, 4, and negative 2, 4, and just, you can look at, you can compare those 3. There's one min and 2 maxes. So when you take 2 out for the local, for the absolute max, it's your level 1, so that it has to be.
Your math.
It's like
changes
all
it.
Your math languages.
Yeah, you know,
Struggle.
first of all, does he have correct conclusions?
Yeah.
Yes.
He's just bad.
Has
You are
bad
math.
grammar.
You
Bad
are
math
bad.
grammar.
And the way that mathematicians learn to not babble is to put their arguments into forms here. So the whole point of all this was to get you to master the form. I didn't care if you could find the conclusion. We all found the conclusion in what, 2 seconds. I cared if we could get the argument into a good form. So,
Am I just missing like the, how I found all the things?
yeah. So let's start with critical points. How did you find critical points?
The first test.
No, you didn't.
Why would you use the test to find the critical points if the test
Yeah.
requires?
It's
I think I'm missing
So let's clean all this up.
definitely missing something.
Oh, goodbye.
Level teachers try to do that and then don't make double circles, so they just have a little dot of erasement.
Okay. So let's start with finding critical points. Tell me how that goes.
He doesn't have to.
For the endpoints, I just, because the endpoints I evaluated,
Let's start with the critical points. Tell me how that goes.
I took the derivative of f of x,
Okay.
and I found it was 2x. Instead of equals 0.
Aha. Notice that this is actually a much more efficient statement than what you were doing before. And this is the right form. So now we have a critical point. Good. Now, let's keep going.
I realized from that function that there were no more critical points on the interior of the function because there's only 1, 0.
Correct.
So then I found the value of f of negative 2 equals 0.
Okay. Now that he's found these things, what is he set up? What kind of argument is he set up to make?
Argument from the values.
Argument from
The values and.
critical points and
Critical
endpoints.
Yeah.
Yep. So now express your conclusion.
Because the maximum value of those 3 critical points is 4.
Yep.
The f, the y max is 4. Then 4 must be the maximum
Mhm.
for over that interval, and so it occurs at 2 equals f of negative 2 or negative 2
And the min?
occurs at f equals 0 and is equal to 0.
Okay. Take a look at the form that we have here. This is all that you need to say. So it turns out you were saying more than you needed to say, and you were not saying the things that you needed to say. This is what you need. How would I do an argument from sine of f prime for the min? If I needed to. He's got a good argument from critical points and endpoints. Let's consider the alternate universe where we argue from sine.
So you take the derivative,
Yep.
sin equals 0, and then you do the little f prime number line thing.
Okay? That's actually not necessary. All that is information for you.
So then what you get is that f of x is less than 0 for x less than 2.
Nope.
You can
F
just,
prime of x, that's why we call it an argument from the sine of f prime. Yep. Is less than 0 for x less than 0. And f prime is greater than 0 for x greater than 0. And what conclusion can I draw from these facts here?
That f of x has an absolute min at x equals 0.
How about f of 0 is an absolute min?
That works too.
F of 0 equals 0 is an absolute min. This is the form for an argument from the sine of f prime. Practice using this form. I can promise that you will need to use one of these two tomorrow, and you just want to be able to skillfully demonstrate the strict legal language while we're going. Last thing I need to hit really fast: concave up, concave down, and inflection points. Okay, what does concave up mean? Turns out there are 3 equivalent things involving f prime, f double prime, and f.
Prime is greater than 0.
F double prime greater than 0.
Increasing.
F prime increasing.
f lies above its tangent.
Excellent.
I didn't know that one.
Yes, so it turns out that all 3 of these are logically equivalent. The reason f lies above its tangent lines is that the tangent line has a constant slope, whereas the curve has an increasing slope.
Amazing.
Okay? Concave down, reverse all these.
Double prime is less than 0.
F prime is decreased.
I will see that one.
So then you can't mess up the natural order. And how it's just to say this.
Yeah.
Ruin the whole system.
All right. Now points of inflection. We can do them from f double prime, f prime, or f. No, 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 no. Never f double prime equals 0. What is it?
Changes.
Changes signs. That's
Sorry.
right.
Oh my gosh.
This one is James. I have the one crap.
I mean, but they just ruined it, so I'm just not.
Okay. How about f prime?
F prime has a local min or max.
Good. Yeah.
Yeah. I feel like
It's like saying that
And alright, Alex.
the f merges with its tangent. Like
F merges with its tangent line.
They like
Yeah.
overlaps.
It actually crosses its tangent
Yeah,
line.
crosses.
Changes.
Yeah.
So the tangent line.
I can draw it.
So the tangent line
Tangent line is.
because it has to go from being above it to being below it. Okay. Good. Well, you know, we weren't able to review everything on taking derivatives, blah, 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 but there it is. The one thing we have till 45?
46.
46. Awesome. The one thing that we needed to review out of chapter 3 that is a little confusing for some people sometimes is the inverse function theorem. Right?
Oh, yes. Don't we love that inverse function theory?
Like I should probably
That's
do
nice.
inverse sine theorem.
Makes a whole lot more sense than it did last year, though.
Yeah. So the first thing is the two ways in which it can be written. In Euler notation, we have the derivative of the inverse of f is 1 over f prime of f inverse. In Leibniz notation, we have dx dy, or the rate at which x changes with respect to y, is 1 over dy dx. We like this.
Can you do an example with?
Yes. Yep. And there are two classic examples you want to be able to do. One of them is the derivative of ln x. Okay? And so here we're going to think about ln x as the inverse of a parent function. And what would that parent function be? E to the x. It's easy, it's the inverse of ln x, right? The inverses are reciprocal of ln x. And so now, if we use the inverse function theorem, we follow the form. And to follow the form, we need an f prime of our parent function, which is going to be e to the x, of course. And so we would now write this as 1 over f prime of f inverse, which is 1 over e to the ln x. Which is the same as 1 over x. That's right. And we're done. If we do it in a Leibnizian fashion, we have y equals ln x. And we are looking for dy dx. So we're going to think of that as 1 over dx dy. And 1 over dx dy is going to be the rate at which x changes with respect to y. So let's take a derivative with respect to y on both sides. If I take a derivative with respect to y on both sides, that doesn't really help us. Let's do it. Now, let's do it the way I originally wanted to do it, which is with implicit differentiation. So we don't really know what the derivative of ln x is, pretend. Then we're going to
what is it?
Never know.
we're going to undo it with an inverse.
Yes.
And now I can say that taking a derivative with respect to x on both sides, e to the y dy dx equals 1. Put that y back where it came from, or so help me. And e to the y is x from here, and I'm done. So this is how we would do it in a Leibnizian fashion. You should be able to do the same process to find the derivative of inverse sine. So if we think about it in terms of inverse function theorem, then we would have our parent function is f of x equals sine x, and f prime is cosine x. And therefore, this should be 1 over cosine of the inverse, which is the cosine of the inverse sine. And to simplify this, we sketch ourselves a right triangle whose angle theta is the inverse sine of x. And to do that, that means that I need to make opposite over hypotenuse be x. So that sine of theta is x, theta is inverse sine of x. And that means that this third side from Pythagorean theorem is this guy right here, and the cosine of this triangle is going to be root 1 minus x squared. And there you go. You should also be able to do this with implicit differentiation in Pythagorean theorem. Pythagorean identity.